Hello, everyone. It's a pleasure to be here. I would like to. Sorry. Ah, sorry.
How do you want to be strict? So I wanted to give you this meeting straight.
Okay, no problem.
You can talk to us, but that's not it.
Unofficially. What's a joke?
Okay, go ahead.
Okay, so yeah, it's a great pleasure to be here. I would like to talk about our attempts to improve in learning of grammatical descriptors of protein sequences using contact maps. So as it is well known, proteins are strings of amino acids, and because of this, they can be analyzed in terms of formal languages. And if there is a language, then we can hope that there's also a grammar. And if we are in protein world, then this grammar should probably somehow take into account physical-chemical features of amino acids and interactions between them. And what kind of grammar should be to take into account this kind of features? So traditional hierarchy of languages distinguishes four classes of increasing expressivity and complexity. Regular languages allows, or regular grammars allows modeling simple concatenation and recursive patterns. Then context-free grammars adds nesting and branching. Context-sensitive grammars allows for overlapping and crossing interactions. And even if we analyze such a simple case, this schematic representation of a prion domain, we can see that even this very simple structure would require a context-sensitive grammar to be fully expressed. But context-free rules can by itself express some interesting features of the structure, and patterns which are result of the structure can be also modeled with regular grammars. So indeed, it's not that surprising that the most common in the field are models which are at the regular level of languages. And in fact, profile HMMs are weakly equivalent to some subclass of probabilistic regular grammars, and they are great for similarity searches. And well, you can't deny that they cannot model distant interactions. Potts model and related formalism, which are used in direct coupling analysis, they can be considered as a kind of extension of HMMs, yes, because they model interactions. But both methods they are useful when we consider evolutionary related families of proteins, and they are designed for this purpose, and they are great in it. But sometimes we may need to go further. Yeah? We want to model something which is beyond evolutionary conservation, and for this purpose, this is where grammars which are more flexible, which are not based on alignment, can be useful. In fact, there have been, of course, some work on it during recent 20 or 30 years, but it's much less work, much less solutions than in this part of the scene. One interesting model is regular protomata of Costa and Kerbelek. And but of course, ideally, we would need a model which is on a context-sensitive level, or even above. In our case, we focus on context-free grammars because simply because it's a kind of trade-off between complexity, which is probably too high with context-sensitive grammars, and expressivity, which is too low if we use simple regular grammars. A basic descriptor generated by context-free grammar is a parse tree or syntactic tree, and it's useful in in natural language processing. It's useful in RNA structure prediction, but it's much less applied in a protein sequence analysis. But I think we can expect that this kind of descriptors should be can allow for instance, prediction some topology of protein structure, at least roughly. Okay, so as I said, there have been some previous work over years. Some of them quite nice and quite well developed, but it's still well, it's hard to compare it with what we have in with HMRs, for instance. And well, this is kind of ultimate goal. It would be nice to have a method like a tool like HMR. So you put sequences in it and you get grammar, and this grammar is good for similarity searches, but it also gives you some structure, yeah, of a sequence which can be derived from a parse tree. Why it is so challenging? Well, the main challenge is, of course, intrinsic in the data. The physical interactions between amino acids are complex and collective, and to much more extent than in RNA. And alphabet is larger, and altogether it makes computational complexity of processing this kind of grammars for proteins, and especially of learning them difficult. So our goal is to facilitate learning context-free grammars for proteins using contact maps. But before I go to our contribution, it's probably a good time to give some definitions. So probabilistic context-free grammar is a tuple which consists of an alphabet or a set of terminal symbols, a set of variables, or non-terminal symbols. Then there's one distinguished non-terminal symbol, which is a start symbol. And then we have a set of production rules and their probabilities. And using such a grammar, these grammars can be used for deriving a sequence. So beginning with the start symbol and rewriting it with rules, we finally get to a string of terminal symbols, our resulting string, sorry. Each step of derivation is equivalent to adding some nodes and edges to the syntactic tree graph. And the probability of this syntactic tree or of equivalent derivation is simply a product of probabilities of rules which were used in the derivation. Okay, so this is probability of a single tree, but if you want probability of a sequence, it's a sum of probabilities of all trees over the sequence. So now we can formulate a learning problem or estimation problem for PSFG from positive samples. Yeah, so we have a training set, hopefully good representation of the target set, and which consists of sequences, and over these sequences we can have a set of syntactic trees over sequences, and in fact this is something what is used eventually in a learning process. So in general case, to estimate estimation problem can be defined in Bayesian terms as follows, and this term is constant, and if there are no a priori biases on grammar structure, this is also constant. So in fact, this argmax is often only over this probability. And if we assume independence of samples in a training set, the maximum likelihood formula would look like this finally. Okay, so it works. Yeah, there are papers. There are some methods to how to do this. These grammars are inferred. Oh, sorry. There was one thing I haven't said. So it was the general case when we estimated all parameters of of a grammar, but usually a problem is confined to estimating just probabilities. So this part is fixed, and we only estimate this. I will stick to this confined case for the sake of simplicity, but the framework we developed is applicable to general case as well. Okay, so as I said, this method works, but not that greatly as we would like to. So now the goal is to improve it somehow. And in grammar inference, the method of choice for improving learning will be constraining through some structural constraints in training samples. So the best structural constraints are in fact syntactic trees. So if we can learn not from sequences, but from syntactic trees, that's the best option, but it's not always available. So the kind of possibility in the middle is to learn from partially bracketed sequences. Yeah? So this is a case where a set of trees over a sequence is just partially constrained. There are some points where we put some constraints, but other are not. Other are free. This approach works for a natural language. It works for RNA. So our idea was, okay, why not to try it for proteins? And for proteins, the natural source of constraints can be contact map. Okay. So to make this idea, to implement this idea, we define, we say that syntactic tree of a sequence has correct topology or is consistent with the contact map if each pair of positions in contact, according to the map, is not far away, is below a certain distance in a tree. That's our constraint. And with these constraints, it's not difficult to adjust the learning problem in this way that now we learn only from these trees which are consistent with the contact map. It doesn't change too much here. What's also interesting with this definition, we can define some contrastive estimation. What is contrastive estimation? Normally, maximum likelihood estimator, it tries to shift the probability mass from everywhere onto the target sample, on the training sample. And with contrastive estimation, we assume that that when we will be testing, our sequences will only come from either target sample or its close neighborhood. So if we can define this neighborhood, then it can be used in contrastive estimation in this way that that we try to find such a grammar which maximizes probability, of sequences in our sample among sequences in the neighborhood. And there are at least two interesting neighborhoods in our case. One interesting neighborhood is a neighborhood which consists of all syntactic trees over sequence, and this can be used. And contrastive estimator with this neighborhood can be then used for assigning a good parse tree to a sequence from a target population. And another interesting neighborhood is all syntactic trees consistent with a map over any sequence of the length the same length as our sequence X. And this can be used when searching for similar sequences when there is one map in common for all population. Okay, now I'm going to some results. So this is our setup. We will learn probabilities for small covering grammars, very small. In fact, we'll use genetic algorithm, which was successful in our previous works, and we will test on this 3 samples. these are two binding site samples, binding site sequences, binding site motifs, and there's one prion motif. They are relatively simple, but this is because we wanted to test methodology and we don't want some confounding things. And predictive power will be assessed with regard to to negative set which we used in our previous work. So how it looks with predictive power. So this is the baseline, so maximum likelihood estimator against tested against sequences. And the best results were obtained by contrastive estimator. It's not surprising because in this case, okay, we learn with a map, and then when we test, we also use the map because this is the same a priori known map. Most interesting is probably this because this is maximum likelihood estimator, which is learned with the map, but then it is used when testing without map. So this is most general case. And if contacts were, I would say, relevant to the structure, results are quite good, or even very good. Like here, are very good. I mean, improvement. There is improvement with regard to the reference. If contacts were not that relevant to the motif, to the fault of the motif, then results were not that good. Okay, and here is some evaluation of the explanatory power. Improvements are even more pronounced. Yes, here's the baseline. Some grammars didn't. You can't see any resemblance of the tree structure to the contact map. But then when we apply our learning with contact map, we got quite good recall. This is exactly what we tried to learn. We wanted to learn good recall for the training map, and this is when we compare structure of the obtained parse tree with PDB structure, and instead of recall, I give the value of precision or PPV because this is what is usually used in the field. And also we have nice improvement. This is kind of summary that explanatory power was always better. Predictive power, it was more or less the same or better, or sometimes worse, depending on how much these contacts were relevant. Here are some medium quality trees, and we also can see some improvement. So for now, this framework is, well, it's more like a promise than a complete solution, but I think that some theoretical grounds are sound, are good. We are in a process of further testing, so we test on sample sets with individual contact maps, with variable length sequences, and this result looks also quite good. Then we try to learn some descriptors for metafamilies of motifs, which is harder task, but there are some positive results, but it's more mixed and it's too early for validation, for evaluation. We work on better interpreting, so using pairing potential instead of most likely tree, and we will soon make our software publicly available. So here is a list of people which were involved, are involved, or will be involved in a project. Thanks to all of them. And before I thank you, I just would like to invite to a pair of conferences in Wrocław, in Poland. Just before ECCB, we have some great keynotes, affordable prices, and food is in price. So, okay, thank you very much for attention.
Pairwise interaction, but the main problem of using it is that if there is, the structure is somehow nested and doesn't look like a nice pairs of amino acids, but rather like a complex. Will it work on more difficult cases?
So, well, basically, if it's context-free grammar, it's hard to.
So that's
Yeah, but then there's, well, you can think about learning a set of grammars, set of context-free grammars, and each of these grammars will cover part of interactions. Yes, kind of. You can try to have some subsets of interactions which are context-free compatible. So this might be a kind of way through. For instance, we tried in the past, and we will try it again for this framework, using not training one grammar, but to train a couple of grammars, which were each of them was based on different physical-chemical properties. Because here it was everything was automatically learned, but in our previous approach, we fixed some lexical rules which goes from variables to terminal symbols, such that they represent some levels of physical-chemical properties. And well, there are many physical-chemical properties, so you can do many sets of this kind of rules. So, so it was a natural way to generate a set of grammars, and then we combine it simply by averaging. And in fact, the results of this combined grammars were better than results here. I present it here like it is because this is most simple, but yeah, we have some ideas how to make it better.
So thank you again.